So we've discussed the primary components of a fluid power system, the pumps, the valves, the actuators. There's quite a few other components that we need to make them work well, or at least to last a while. And we'll look at a couple of those here. Specifically, we're going to take a look at reservoirs, at filters, and we'll look at a little bit on lines and how we calculate losses in the lines. And I'll show you a couple other things just to give you an idea of where we could go and the kind of things we can do with the fluid power systems by looking at accumulators and some pressure intensifiers and different things like that. So, that'll be kind of stretching your imagination a little bit, give you an idea of the kind of things we can design into these systems. But first of all, let's talk about reservoirs. So what does a reservoir have to do for us in a system? So a reservoir is a storage area. Couple main functions of the reservoir. First of all, the reservoir has to have enough oil in it to supply the needs of the system. Now, a lot of our systems are closed, so it means when the oil goes out or the fluid goes out to run through an actuator, we've got some fluid coming back. But if you think about the cylinders, the hydraulic cylinders that we just looked at, if I'm extending that cylinder, it takes a certain amount of liquid, of fluid, to be able to extend that cylinder. Well, as the cylinder extends, you've got fluid coming back, but think about the volume on the other side of that cylinder. Remember, that rod is in there, so the amount of volume that I displace out of the cylinder that comes back to the reservoir is less than what went out. So if I extend that cylinder, the level of my reservoir actually goes down because I'm taking more out than I'm putting back in. So that would be a case where, hey, I've got to have a little bit of reserve in there to make that happen. Now, if we have single acting cylinders, it's even worse. So I send the fluid out to extend the cylinder, there's no return coming back. I got to make sure I've got enough in my reservoir that I don't run the reservoir dry. And so that's one of the fundamental considerations of a reservoir, is just simply volume and what I could be using. But probably the other major function of a reservoir is for cooling. Remember, I talked about the fluid power systems. They're terribly inefficient. They can be. There's a lot of waste in them, so they build up a lot of heat. And that heat gets transferred into the fluid, and that ends up back in the reservoir. And so one of the functions of a reservoir a lot of times is for cooling, to be able to cool that liquid down, to be able to dissipate some of that heat away. So, and we'll talk about design and how we do that in just a second here. I'll show you the equation. The other thing that we look at with the reservoirs is with the contamination removal. So through the system, we have valves and how there's no seals or anything. It's all very tight tolerant. As things move, we're going to get some wear. We may pick up dirt in the system from other places. So for instance, in agriculture, we have those remotes on the back of a tractor that we can plug hoses into. And if we don't clean the hoses off before we plug them in, all the dirt that was on the end of the hoses goes right into the system. So we have some opportunity in the reservoir to be able to remove some of those contaminants simply by slowing down the liquid. And those of you who had the hydrology classes, soil and water type classes, you know that, hey, when the velocity is high in a stream, it's going to pick up sediment and carry it along. If we slow it down, that's where the sediment drops out. And so we do the same things in a fluid power system. We slow it down and let it settle in that reservoir, and hopefully some of those contaminants will settle to the bottom. So let's take a closer look at the reservoir. I'll talk about a couple things here on how we design these things and what is critical for in the reservoir. And I'm going to draw a picture of a reservoir, side picture. And again, the JIC symbol for a reservoir, you've seen it in a lot of these circuit diagrams. It's very simple. It just shows it like this, and that's basically a tank. So I can pull out of the tank and go back into it. But there's some subtle things that we need to understand. So here's a side view of this tank. So I'm going to draw the tank there. I'm going to put the liquid level in here, a little bit over half, so I'll show that as the liquid level. So that's the liquid in this tank. And a couple things to think about. So where am I going to bring the pickup? So if I want to take the liquid out of this tank, go into a pump, where would I put that pickup? So a lot of people think right away, hey, let's just put it in the bottom. So it pulls the fluid off the bottom, and that's going to go to our pump, all right? Is that a good idea? Not really, because what did I just say? The contaminant removal, we'd like to have a lot of those contaminants, the shavings and metal shavings and whatever dirt we've picked up, we'd like to have it settle on the bottom of this tank. So if it settles on the bottom of the tank and I'm pulling out of the tank, guess what I'm doing? I'm just sucking all that stuff right in there and it's going right through my system again. Bad idea. So what I typically do is draw out of the side of the tank. I've got part of the tank that is going to be below my pickup that I'll never be able to use. I'll actually never be able to pull out of that, but you can see it on the side here. So this big port on this tank is on the side, but there's a little bit of space below it, so I don't drain it completely. I'd have to put a plug on the bottom then of some kind to be able to drain the tank, to be able to change it and clean it and so forth. But that's where my pickup would be. Now the other thing I think about is where do I bring it when it comes back? So it goes out through the system and it comes back. Where do I bring it? Well, a lot of people say, hey, let's just dump it in right there. Okay, so we bring it in the top, we dump it in, and that's great. All right, but it's not great because think about what happens. I got a lot of fluid that's coming back through here. It's hot fluid. And I dump it in, it's going to spray, it's going to hit down here, it's going to splash, and what's it going to do? It's going to create little air bubbles in here when it splashes. Air bubbles are a really bad thing for fluid power systems. If they don't pop and dissipate, which if I have a fairly viscous fluid, they're going to stay in that fluid for a while, and they could actually be carried right down here to the intake. And now I carry these air bubbles into the pump. If these air bubbles get into the pump, when they get into the pump and get subjected to the high pressure on the pressure side of the pump, they will collapse. And they'll actually, when those things collapse, they create a large force and they can actually pit the metallic surfaces of the pump, so they can damage the pump. So air bubbles are a really, really bad thing. So we don't dump from the top back into the reservoir. We actually bring it in from the side. So we like to bring it in below the surface so that it comes in, we don't splashing, we're not being turbulent. Then we'll often put some type of a barrier in here of some kind, so there's usually some things like that inside. What'll prevent this oil from short circuiting, which means it goes straight from here over into the intake. So we don't want this hot oil to go right straight back in. We want it to sit in here to mix, to have the opportunity to cool before it can move over here to go back into the system. So we'll do some things like that. So the reservoir design, there's actually some thought that goes into it. Now in terms of heat removal, I said I'd talk a little bit more of that, and you guys have seen this heat equation, E equals mc delta T, right? So the mass, so the energy, the thermal energy that's in that oil is the mass of the oil. The thermal coefficient, which the thermal coefficient, if you remember, it's the number of kilojoules it takes to raise 1 kilogram of fluid 1 degree Celsius. So it's kilojoules per kilogram C, okay? So that's the C factor, so that's the thermal coefficient of the fluid. And then the delta T. So if I can know how much the temperature has changed, I know how much energy I put into it. Likewise, if I know what my losses are throughout a system, so I could look at a system and say, okay, my pump, I'm putting so much power into the pump, and I've got so much coming out of the actuator downstream, and there's going to be a difference in between. All of that difference, there's a good chance that a high percentage of that is going straight into the fluid. So I would know then how much energy is getting put back into this reservoir. So I would know how much it would heat up. Therefore, I would know how much I'm going to have to dissipate off of it. So I can know something about the surface area. If I know the heat transfer coefficient of this reservoir and so forth, I would know how big to be able to make it and how much I could dissipate it off. And I may, in terms of heating, I may actually have to build a cooler into it. So sometimes we'll actually build a heat exchanger, a radiator, and a lot of vehicles will have extra radiators in front of the engine where the engine fan moves air through it, and that'll cool off the oil before it goes back into the reservoir. So sometimes if the reservoir is not big enough, we may need some additional cooling then to be able to cool that reservoir off. So that's just a little bit about reservoirs. And by the way, an interesting thought about reservoirs is that a lot of these reservoirs, if you look at an agricultural tractor, the reservoir is the transmission. So the gears and so forth, the fluid, the oil that lubricates the gears is the same fluid that we use in the have one big reservoir. So it is actually multifunctional. It provides the lubrication, the cooling for the transmission, and in fact a lot of our transmissions now are hydraulically activated, so they're not old school shifting and grinding gears. They're using switches and levers, and it's all hydraulically activated with clutches and things like that. So there's a lot going on in modern machinery, modern mobile machinery. So that transmission is also part of it. So that's reservoirs, and a little bit that goes into the design of reservoirs and understanding that. Let's talk about filters then a little bit. And filters, we got this contaminant problem. We've got to get the contamination out of the system. So we can't rely on just a tank settling it all out. There's going to be stuff that we have to actually forcefully filter out. So there's some examples of a couple filters there that you see on the left, different kinds. So they can be different sizes and so forth. So let's dig into this a little bit. Couple ratings, things that we understand for filters. The primary rating of it, we talk about the micron rating. What is the micron rating of a filter? Micron is a micrometer, all right? It is what it says it is. And that's basically the size of the holes that are in the element that the oil has to go through. So the fluid has to pass through this element. There are holes in it, and the holes, it's designed specifically with a certain size hole that's going to trap certain size particles. And we would have to know what the nature of our hydraulic system to know what size filter we need. We need to know the tolerances on all our valves and the clearances and everything. So we want to filter out everything that's big enough to get caught in a clearance in any part of our hydraulic system. So that's where we would design that micron rating. So typical small filters are on the order of 50 microns or something like that. And then they would go up from there, so bigger ones. Okay, there's the JIC symbol for the filter, just a diamond with a dotted line across it. But the question is now, where do I put it in the system over here? And I have a lot of options. So I could stick it here, and here's one logical place to put the filter. So I'm actually going to draw it in here and show a filter in the system here. Here's another logical place for it out here. So I'm going to draw another filter down here. And here's another logical location. So 3 different locations that are logical that we could put this in the system. Now, why would we want to put them in those different places? Well, let's start at this first one here. Let's start at number A. So what do we think about A? Let's label these A, B, and C, and let's talk about each one of them and why we might want to put each one of those in those different positions. So first of all, let's think about A. So position A, it's got the advantage that we see that position, the fluid sees that filter before it ever gets to the pump. So the pump is one of the critical components in our system that has really tight tolerances, and we saw some of those pumps and everything. So if I get dirt going into my pump, I'm going to damage my pump. And so it'd be nice to catch all the dirt. You know, maybe we got some dirt in the reservoir when we were filling it. We weren't careful. Somebody left the lid off or something like that. We don't want that contamination going into the pump. And so we could put a filter there at position A. The problem with position A is that's before the filter. There's going to be before the pump, there's going to be a pressure drop across the filter. Anywhere we put it in the circuit, there's going to be a pressure drop. So live with it. Suck it up, buttercup, is what we say. So anytime we put a filter in there, it's a loss of power. That's why in all our equations we keep talking about delta P. So we have to look at the pressure drop that is available to do useful work. So if I want to look at the pressure drop across the motor, I have to look at the pressure that is on the inlet of the motor and the pressure at the outlet. So that outlet pressure a lot of times will have to go back through filter and valves and all that kind of stuff. So that's the delta P. So it's a power loss, we have to deal with it. But the other critical thing is when I'm drawing that through that position A, it could get a negative pressure, it could get a vacuum. So if I have a vacuum, a large enough vacuum of that fluid coming into the pump, we'll get a situation that we call cavitation. And that's where we draw a low enough pressure, we draw a vacuum on a fluid, and you know when you draw enough of a vacuum on a fluid, you can actually make that fluid vaporize. So we'll actually vaporize little bubbles or little droplets, if you will, of that fluid. And so we get these vapors, and I mentioned before, if those little bubbles or droplets, vapor droplets, vapor holes go through the pump, they will collapse when they get into the high pressure side of the pump, and that collapsing can actually damage the surface of the pump. So it actually pit and corrode the pump. So it's very noisy, it squeals when it does it, and it can be very damaging to the pump. So you don't let that happen very long. So that's a bad part about putting it at position A. All right, so let's move around. What about position B? So position B is nice because, hey, it's beyond the pump, so I don't have this cavitation problem. I'm not going to protect the pump. You know, I might get some dirt in my pump, but I'm going to protect everything else downstream. So I'm not letting any dirt get downstream. So that's a good thing. So I protect all my valves, all my actuators, and everything else, keep it clean there. So that's a cool thing. The problem is, let's think about the pressure in that part of the system. So that's right after the pump. That's where I'm going to see the highest pressure, highest system pressure. So that changes the design of my filter. So if you look at that filter on the upper left, that's just a very thin sheet metal canister. And if I put that in the high pressure side of my system and my system pressure gets up to 2,000 or 3,000 psi, it goes boom, so it won't take that. So I'd have to have a very expensive high pressure type of a canister, and that second one down there is kind of a high pressure type canister, so it's got to be a very heavy wall, it's got to be sealed to be able to do that. Now we do have applications where we'll use them there, and we have some systems that I've used in the field for some precision agriculture stuff, and they had very sensitive valves. And those valves had very tight tolerances in them, so we had to protect those valves. And so in those systems, they specified putting a high pressure filter right before that. So it's an expensive filter to handle those pressures, but sometimes we have to do that to protect those very sensitive components. So that would be the disadvantage of putting it in position B. What about position C? Position C is nice because it's right before the reservoir, so we're going to keep the reservoir clean. So any dirt or materials, particles that we pick up in the system from wear on the components or dirt that we introduce somehow, we're going to catch it before it ever gets into the tank. So we keep the tank clean, and that's a nice part about that position C. The problem is any dirt that is in the tank, that gets in the tank, we don't get. It has to go all the way through the system before we can catch it. So, all right, advantages and disadvantages. What do we do? Well, typical practice in most fluid power systems is that in position A, we put a relatively large filter. So this is the one we're going to catch the big boogers, if you will, the big chunks, and not allow them to go through the pump. So typically 150 micron or something like that, maybe bigger. Then in position B, we don't use very often unless, like the example I gave, we have to protect some sensitive component. But usually we put a second filter then in position C, and that takes out all the contamination we picked up as the fluid moved through the circuit. That's going to be a smaller filter. We're going to try to keep our reservoir clean. Hopefully we'll manage the reservoir in a way that we don't introduce dirt into the reservoir as we go. So that's the more logical place to put it, put a second filter. So typically in a larger filter in position A to protect the pump, keep the big chunks out. Position C then is the smaller filter, the 50 micron type smaller filters to clean things out. So those are filters. Again, the thing when we're designing, we always got to realize anywhere you put it, it's a pressure drop. So if it's a pressure drop before the pump, that means the pump is not going to be able to develop as much pressure. It works on a delta P. So if it's got a vacuum in front of it, its gauge pressure above ambient is not going to be as big because it works against that pressure difference. Okay, likewise on the return in position C, I'm going to have some pressure drop across it. So whatever system pressure I develop on the top side of that motor, the return has got to be able to push fluid back through the filter. So there's going to be a couple hundred psi drop maybe across that filter depending on the size of the filter and if it's plugged up or anything like that. So we have to deal with that anywhere it is in the system. So that's the thing we have to remember. So that's filters. Necessary evil. We have to put them in the system, but to protect our system, so they've got to be there. All right. Now, lines and losses, I'll talk about this briefly, but your book does a great job on showing some examples of how to do this, so I'm not going to take lecture time to do that because you can read the book, and it's pretty straightforward, plug and chug how we do this. And you've had, most of you have had your fluids class, so you've done this, you've looked at the Reynolds number that we have there in the first equation, so you know how to calculate Reynolds numbers, and the book gives you the units and everything to make that work out pretty nicely there, so it can be a pretty simple plug and chug for you. But then there's a couple equations there to develop, to be able to calculate what the pressure loss is. And if you look at these equations, let's dig into them a little bit closer. Reynolds number there, they have two different equations. Both of them give me a pressure drop per unit length of our line. All right. The top equation is for laminar flow, and the bottom equation is for turbulent. And you probably remember that those laminar and turbulent flow, the definition comes from the Reynolds number, so you calculate that Reynolds number. If it's greater than 4,000, that puts me in the turbulent region. If it's less than 2,000, that puts me in the laminar region. If it's between the two, it's really ugly. You're taking a guess. Nobody really knows what goes on in that region in there, and so frankly, what I usually do in that region is I just say, oh, it's turbulent because that's probably going to give me a bigger pressure drop, and that'll be the more conservative estimate. But again, your book has some really good examples on how to do that, so I'll let you read that and go through those examples when we have some homework practice and stuff with that. Now, the other thing that your book does is looking at other components in the system like elbows and things like that. And the way they do it, they have a way, the simplified way, where they actually convert that those different constrictions, so bends and so forth, they convert them into an equivalent length of pipe. And so you would find that equivalent length, and then you would come back to one of these equations and calculate the pressure drop based on the equivalent length of line that would be there, that it would be associated with. So we can add in bends and other things like that, elbows and so forth, to be able to get the pressure drops on those. So again, pretty straightforward, pretty simple. I'll let the book do that for you. A couple other things I'll mention, and we're not going to do a whole lot with them. Accumulators, and go back to the circuit analogies. Accumulator is a capacitor. It's a storage element. And so, maybe this will help you in your circuits class to understand what a capacitor is. So I can put fluid into it as I pressurize it, and then it's held in that thing at a pretty high pressure. So you can see the designs on the right-hand side, and there's a lot of different ways that we can put them together, but generally we have some type of a bag or a bladder in there, and we usually have some gas in behind it, and we can pre-charge that. Sometimes it's charged with nitrogen, sometimes we just put air in it, and then we have a way from the bottom to be able to push fluid up into it. So we just push fluid in, it compresses. At the higher the pressure, the more fluid goes in, it compresses this bag, and then the fluid can come out. We can do a lot of neat things with them. And in this circuit that I show on the left here, this is the symbol for the accumulator in there, and it just shows the fluid coming up in. This is a case where we can actually use the accumulator to help me make a cylinder move faster. So in this particular case, this pump is going to push fluid over here, push it through the check valve. It'll charge up the accumulator, so it'll charge the accumulator to whatever volume of fluid I can put in there at the system pressure. Once it gets full, then the relief valve will open and it'll dump off. Now, when I open this valve over here to extend the cylinder, now I have this charge of fluid in the accumulator at a high pressure. That fluid can come running out. It won't go back to the pump, and it can extend this cylinder. So I can get a big burst of energy. I can move that cylinder really quickly at a higher rate than what this pump would be able to deliver. So I can use a relatively small pump if I have a cylinder I know I'm not going to be using it real often, just once in a while, but I need a really fast movement there, so I can use that to charge it up and move it pretty fast. So some cool things like that we can do. The other thing we can do is actually stick them on the other side, on the cylinder side, so we can put an accumulator over here and build it into there, and it becomes like a shock absorber. So we can actually absorb some shock when we have heavy load on the cylinder out there, so we can build them to do that. And I've seen these used, and again, some of my experience with on sabbatical with the major equipment manufacturers, big sprayers that have really, really long booms. You know, they're 120 foot long, so we have a 60-foot boom that's cantilevered out there, and we start hitting bumps, and this thing's bouncing around. Well, it's tearing the mechanism apart because, you know, all those vibration loads and impact loads on the structural framework part of that machine. So if we build a hydraulic cylinder in there with the accumulator, we can make it like a shock absorber, so it can absorb some of that shock, you know, take some of the fluid from the cylinder, go into the accumulator, build up the pressure, absorb some of that pressure, allow it to come back out. So it's almost like a suspension on a car. So it's a similar concept to a suspension. So a lot of neat things we can do with accumulators there. Again, we can design those things, we look at volume, we look at pressures and so forth and what we need to do with them. We're not going to get to that detail. We're just not going to have time in this course to be able to do that, but at least wanted to show you that. And we could go crazy. I'll show you one more crazy kind of thing we could do. This is called a pressure intensifier. So I may have a situation in a circuit where I need a real high pressure, and I can sacrifice flow rate. So I have a lot of flow rate available. And so basically, like you see in the upper left, is a concept where I have two cylinders that are connected together, a large diameter cylinder and a small diameter cylinder. So what I do is put in a lower pressure, and they're showing in this example 3,000 psi coming in here. It's acting on this large cylinder, so I'm developing a really high force. And that really high force then is acting on a smaller cylinder, so I can get a whole lot more pressure out of it, okay? So as this cylinder moves from left to right, I'm going to have 6,000 psi available over here, twice the pressure, but the sacrifice is I only have half the flow rate. So this is, again, go back to the circuit analogy again. This would be like a transformer in a circuit. So I can have a step up or step down transformer where I can step up the voltage. I can make the voltage higher, but what's my sacrifice? I don't have the same current available. So in this particular case, I can step up the pressure. I can have a real high pressure. I can lift a heavy load, but it's not going to lift it very fast. The sacrifice I'm going to make is in flow rate. So power, pressure times flow. I can't create power. If you can patent that and retire and live large. But whatever power I have available, I can transfer its form. So I can make it lower flow, higher pressure, higher flow, lower pressure. I can do some things like that with it. So that's what we use pressure intensifiers for. So just a couple things there just to pique your curiosity and give you an idea of some of the designs that we can do with it. So next thing we'll do is actually take a look at some systems. Let's start putting this all together and see how systems work together.